since the late 90s. I'm also a trainer for ProTech, doing some Java courses, and I'm the author of this book on the left. If you want to learn about functional programming in Java, and also more recently a video on JPMS. This, if you want to learn how to do modularity in Java, you get that on Linda and LinkedIn Learning. All right, so let's get started. So Java's been around for 22 years. Very different context than when it came out in the late 90s. The concerns we had were very, very different than they are right now. At the beginning of the internet, there's been 10 versions released in that time. This was under the stewardship of Sun and later on Oracle. Quite a big community has been built up, 8 to 10 million developers by latest accounts. And it's become really the very dominant language on the web, on the cloud, on mobile. And it's also a platform. So not only is it a language, but it's also a successful platform for other languages that compile to bytecode. Examples of that are Scala, Groovy, Kotlin, and Clojure. So by all accounts, a successful platform. And so you might come to the conclusion that there's no need for improvement. But the reality of that is that there's actually been an acceleration in terms of new features that have been added just in the last 4 years alone. So if we take a look at that, we have things like functional programming, which have really changed the way we program in Java, reactive programming, multi-core parallel programming, JPMS, streams, JShell, promises, a lot of things. And even the language itself, syntax-wise, keeps evolving. We see things like Project Valhalla, Coin, and Amber, and these are bringing changes. And if all that wasn't enough, there's also a brand new release train model that's been announced recently by Oracle. What this means is that there are not going to be new releases every 6 months. So typically what we had was releases every 2 to 4 years, but the pace now will be accelerating. So in the past, we had features that would delay releases. We've seen that with Java 8 and Lambdas. We've seen that again with JPMS and Java 9 with modularity. And so all that it will be changed now. And the train leaves the station every 6 months. And if the features are ready, they make it on the train. Otherwise, they wait for the next scheduled train, which is every 6 months. So what that means for everyday Java developers is that we have features that are available sooner. There's more rapid change, and it will change the way we think about releasing software. So, and this has kind of ushered what I like to call the new age of Java, or the modern Java. We have classic Java, which represents Java 1 to 7, and the modern Java, which I would consider to have started at around Java 8, 9, and 10 and beyond. In my consulting practice, I work with different companies, and I still see many companies that are still stuck in Java 7. And so for those developers, once they do migrate to Java 8 and beyond, some parts of it are actually unrecognizable. So there's been a lot of changes that have occurred in the last few years. And so this is really the kind of the setup for this webinar. So we've seen this, there's been new syntax, new libraries, new programming paradigms, and deployment option. And this is why I'd like to talk to you right now about 5 ways you can modernize your Java code right now. Let's start with number 5, streams. So streams were added to the language back in Java 8. And I would consider this to be probably the most important feature in all of Java's 22-year history, because they really changed the way you program in Java. And streams are really 2 different things come together. They're the realization of functional programming in Java. So what I mean by that is that without streams, you wouldn't really be able to reason in terms of the functional programming paradigm. So streams is where that happens. Yeah, we have lambdas as well that is part of the syntax, but streams is where all the things about statelessness and thinking about functions as a first-class citizen of the language, this is where they really come to life. The second thing about streams is that they're core-aware parallel processing. It's a core-aware parallel processing framework. And so this is what allows you to use multi-core technology that we see in modern chipsets. So let's take a look at both these things. Let's take a simple example. Let's say you'd like to write an algorithm that determines if your number is prime or not. So this is the way you would do with streams. So you think about this using 2 different boxes. So you have a range closed and a none match. So the range closed is the way to iterate from a given range, from a start to an end range. And as we can see in this example, we're iterating from 2 to the square root of the number we're trying to test for. And then we apply a lambda called the none match, and we're looking for this condition that none of the numbers must match. In other words, no number must be divisible other than by itself. And so if that returns true, then we have ourselves a prime. It's a prime number. So you can see from this, it's very different than how you would traditionally program in Java using for loops or while loops. This is a great example of the declarative programming that streams and functional programming brings to us. We think in terms of boxes. I need a range close, I need a none match. And I would argue as well that this really communicates intent a lot more clearly than your traditional while loops or for loops. They're easier to test as well because you're not actually doing the plumbing code. You're just fitting in that little lambda. That's your job, and the rest of it, all that iterating and the none matching is actually done by underlying framework. There's also two other benefits, and this is conciseness and parallelizable. We'll come back to that in a minute or so. There are also some caveats, of course, as with anything else. When you program with streams, they're functional animals, so you have to think in terms of statelessness. You can't do whatever you want to do, and that's kind of the trade-off when you're programming with streams. You got to do what the Stream API gives you, and there is a learning curve that comes to that. So in the modern Java class that we're going to talk about later on, we do spend quite a bit of time learning how to think in terms of streams. So that's part of the steep learning curve. Then there's also conciseness, which is a benefit, but also a caveat, because especially when you're new to this, it may seem a little bit foreign, and the conciseness can actually look scary. And then finally, the parallelizable, which is a benefit and also a caveat. Let's talk about that one right now. When we have on the left the serial stream, that's what we just saw before. The right is when we ask for the stream to become parallel. We just add that little keyword that you see right there, the little method called parallel. We can add that anywhere in the line, and it gives us instant parallelization. And what happens graphically is what you see on the right. So essentially, the Streams API automatically performs the none match calculation in parallel, and it does that for you. You don't have to actually program that. You just ask for it. You say, I want my stream to be parallelizable, and that's the declarative aspect of it. Then there's also the aggregation that happens by itself. So it's got to reaggregate the results of each individual streams. You can also take this to the next level and say, you want to find the range of prime numbers from, let's say, 1 to 1,000,000, and then you've got this going on, this diagram that shows you. So we got a range closed. You're filtering, and the filter is actually the call to my first stream, as you can see in that little cloud. And you can also call that in parallel as well. So you've got a stream in parallel that's calling another stream in parallel. So all this is possible, and it really changes the way we would traditionally program. When it comes to parallel processing, you need to watch out for a couple of things. The order of what you're trying to do has to be, it must not matter, it must be order independent, because the parallelization can be done randomly, so that the numbers don't come in the sequence that you would expect as they do in a serial stream. You also always have to watch out for the return on investment on what you're doing in parallel. So the stream is doing lots in the background. If you're not doing enough, then you'll be wasting more time setting up the stream to be parallel than actually doing anything, and you'll get worse performances. So you need to watch out for that. So the best examples in terms of performance are those that are CPU bound. So if you're doing calculations, those will give you great results. And of course, you always have to watch out for thread saturation. And what I mean by that is, in our previous slide, we saw how we had one parallel stream with calling another parallel stream, but really both hitting the same executor service. It's actually calling the fork join framework under the hood. So they're using the same threads underneath. So you need to watch out for, kind of going crazy and all that. So I actually have the code examples for this, and I'll show you the GitHub repository where you can grab those. So you can take a look at that offline if you'd like to. Let's move on to the next one, promises. So promises is also something that we see in other languages. JavaScript has that. Most major languages have that. This has also been added as part of Java 8. So very powerful kind of framework. The idea of promises is you weave together interdependent functions. So functions that feed off of each other. You have one function running, and the result feeds off to the next one. You could run these functions synchronously, asynchronously, or even both. I like to call promises really a weave and get framework. So you weave everything together, and then you ask for the result. You're not really caught up in between each of these functions and programming that. You're just weaving together, and then you kind of get out of the way. And I'll show you what I mean in a code example shortly. You can use these to chain functions, as I mentioned. Even you could look at these as stages. So these functions are kind of stages in processing, and they run in parallel or a combination of both. You could use these in situations where you're making multiple network calls. Maybe you're calling different web APIs at the same time, and you want to aggregate the results together and then do something else. There's also a term that comes from the JavaScript world, which is the callback hell. This is how promises allow you to avoid the callback hell, because you're setting up the stages beforehand, and then you get out of the way. So it becomes very difficult to do these kind of algorithms if you're not using promises. So I'm going to show you an example now, which is going to do this particular processing. We're going to talk about, so we'll have 3 different sites that we're going to go scrape. So just a basic HTML screen scraping. We'll just grab all the words that are in 3 different sites. We're going to combine the results together because we'll be running these in 3 separate threads, as you can see, thread 1, thread 2, and thread 3. We're going to combine the result, then we'll catalog the result in a hash map, and then we're going to run the reduction operation or statistics. So we'll just be generating statistics in parallel. So how would this look like in code? So let me just show you a demo. And I'll start with a very simple example, and I'll show you the one that we were just talking about. So if I were to have a promise that has 3 different functions, so we start with the number 2, we multiply by 2, and then we multiply by itself again. So the way we would do this in Java is use the completable future. That's the concrete class. So when we say promises, that's just the generic term. In Java, they're called completable futures, and they extend the future class. We start off with a lambda that generates the number 2, just arbitrary number 2. That is run asynchronously right away. Then we apply another function, which in this case we're doubling, multiply by 2. And then we call it again and we multiply it by itself. That's just one very simple example. I also have this unchecked get. So this is just a get method. So we call the get on the promise. And then here's another simple example where we're just combining hello in there. So if I run this, you'll just get 16, which is the result of 2 times 2 multiplied by itself again. Okay, so that's a very simple example. Let me show you the site scraping example, which has more code, but just bear in mind that to do this without using promises, you would end up with a lot more code than this. This is actually pretty compact. And again, you could take a look at this offline. So I'll go over this very quickly. We start off with our 3 site scraping promises that run in parallel. We combine them, we catalog them, and then we call 3 different stats on these promises. So I'll just go to the part there where I weave together the different functions. So this is my completable future right there, which runs my site scraping function. So this will scrape the first site. We have the second one here and the third one there. The results of all this are combined with my combiner. So I'm supplying another function here that combines the results of my 3 promises like that. That's how I do it. So you notice I just keep using the same combiner promise here. So the combiner promise is what combines the 3 different site scraping promises. So I've got the first one combined with the second one, combined with the third one. And I'm also supplying a lambda that tells you how to combine. So we're always specifying lambdas when we do this. Then we go on to our cataloger promise, which is all it's doing is it's putting this in a big hash map. And finally, we spawn off these 3 different promises like this. We start with our most used promise. So we're taking our catalog and then we're doing an apply on it asynchronously. So you can always choose between synchronous and asynchronous processing. Here we're doing this asynchronously. Same thing with the average length promise, the average length of the word and the total unique words. So just in the interest of time, I'll just run this quickly. So I'm going to be running this on these 3 different arbitrary sites. So I'm scraping oracle.com, dzone, and JAG-Center. There we go. So it ran pretty quickly. It's done. The most used word was div. So that's just the HTML keyword. The average length was 7, and there were 3,494 words scraped. So I do invite you to take a look at this, to really look at what's going on in more detail. Okay, so let's move on here to reactive programming. So reactive programming is the third one on my list. That's something that was added as part of Java 9. And we see a trend in the software industry that the Java folks have paid attention to and have responded to by adding this as part of the language, as part of a library. So reactive programming, what is that? Well, it comes from a so-called reactive manifesto, which is simply a declaration of ideals of what modern software design should be today. So, software keeps on evolving. It needs to get better for the problems that we're solving today. This Reactive Manifesto proposes 4 pillars that all modern software should have. These are responsive, resilient, elastic, and message-driven. So essentially, we expect our software to be responsive. In other words, when we send something to it, we send messages to our software. Even if it's not doing well, we expect some kind of response, as opposed to just not saying anything at all. Resilience, we expect failures to be handled in a graceful way. Elastic, load should, there should be more processing that can be taken, or less processing, and it's able to scale up and down. And finally, message-driven is the idea that each one of these components can talk to each other using messages. So there's an organization called the Reactive Streams that took this Reactive Manifesto and created a spec that realizes some of these ideals. And this is just the spec, the high-level spec of what they came up with, and it's essentially a blueprint for how to implement reactive programming. We'll take a look at this, how this was done in Java. The Reactive Streams also has a spec that dictates how applications should behave in a reactive setting. So I'm going to show you a real example. This is something that I've encountered a number of years ago when I was working for an investment bank. And I think this was something that was before the reactive programming trend, but reactive programming would have solved this problem very well. So essentially what this application did is it received market events. So it's obviously a continuous stream of data that comes in, and you've got a receiver that its job is just to receive these events, to transform them into a particular format, and then put them in a queue. And then there's another process, another thread that dequeues this, and that's the processor. So the constraints of this application are that events have to be processed in real time. So the idea of processing something later on, even 5 minutes later on, is unacceptable, because the investment bank needs to know what's going on in a timely way so it could react to it, of course. Dropping events is also a bad thing. You can't drop events. So you have to process them in real time, and you can't drop them. And this is really where the ideals of reactive programming come in, and they align well with these kind of constraints. So of course, what do you think would happen in this kind of application if the processor is too slow? And this is something that happened. What ends up happening is that the queue ends up overflowing, of course, and then it eats up more and more of the heap of the JVM. It slows down, then the garbage collector starts to thrash because it's spending more time garbage collecting, and there's less and less memory available. So this just makes the problem worse, and it just kind of spirals down until you get an out of memory and then nothing happens. So exactly what reactive programming is saying not to do. So how can reactive programming come? Well, just before I talk about that, the way we solved this at the time was to simply bound the queue such that use a linked blocking queue, such that the receiver there, if the queue gets to a certain size, then it just gets blocked, and it just blocks everything upstream. So that prevents the server from crashing, but it doesn't actually respond to the business needs because you're still not responding to the events quickly enough. Okay, so what can reactive programming do for us? Well, essentially is that we're going to add visibility so that the receiver can know what's going on with the processor. We're going to have visibility at 3 different areas. First of all, how big is the queue? Is there even a processor that's doing something? Because remember, these are asynchronous processes, so the receiver doesn't know what's going on. So the reactive programming adds that. And is the processor healthy? So we have these kind of viewpoints. And conversely, and the other way around, the processor is also able to communicate the control of the events. It can say, it's ready to receive events. It can say to stop sending, and it can communicate that it's actually there doing something. So this is what the framework allows us to do. So essentially, we're just adding the ability for the producer and the consumer to talk to each other. The way that this is implemented in Java, it's fairly simple in terms of the library itself. So it's not a big library. It consists of these interfaces and classes, and they conform to the Reactive Stream spec. So we have a flow publisher, which is the component that produces events, and then we have the flow subscriber, which is obviously the consumer. As a publisher, you have to implement this method that allows subscribers to register themselves. As a subscriber, you have these 4 callback methods: the onSubscribe, onNext, onComplete, and onError. Once you've subscribed, there is this subscription that the subscriber gets, and that's how you control what you're getting. So you can you request elements. You don't just get pushed elements like you would in a regular queue. You have to ask for them, and if you don't ask for them, you don't get anything at all. And as well, you can cancel at any time. The spec also defines a processor which combines the publisher and the subscriber. Now, Java goes one step further and provides a submission publisher, which is a concrete class that encapsulates a queue and allows you, and it's also a publisher, by the way. As you can see here, it implements the subscriber interface. And it allows you to use these 3 methods, so offer and submit. Offer, there's 2 flavors of offer, plus a submit and a subscribe. So this is how you put stuff inside the queue. So let's take a look at another quick demo using that same stock market example, really simplified. So I just want to show you some key areas when designing an application that is reactive. So we start off with our main. It's a very small application, very simplistic, but I think you'll get the general idea. So we have the trade analyzer is the subscriber, the one that will be receiving the elements right there. So we start off with our submission publisher, which is which encapsulates a queue and is also a publisher. We will use, this is one of the flavors of the constructors you can use here. This one here determines which fork join pool you will be using. No, you can also use the default constructor so that you don't have to specify this. Then we have the queue size. Here we're being very restrictive. We're saying that the publisher will only have a maximum buffer of 2 elements in there. What happens when you go beyond 2? Well, it's going to block. So what's going to happen is you're going to start dropping events. And this third parameter here is a lambda that one of the subscribers has errored out. So you get this visibility right there. In this case, I'm just logging the fact that a particular subscriber, in this case, the trade analyzer, has errored out. So let's keep going. We subscribe the trade, we create a trade analyzer, we subscribe it. Let's take a look at the trade analyzer. How does that work? Well, we have our 4 callback methods. The onSubscribe, that's the callback we get as soon as we subscribe. We got to keep a reference to the subscription, and it's right there. There's a subscription, and you have to ask for elements or nothing happens. Every time you get an element, that's your callback method, the onNext. So you get a message, you process it, you ask for another element. The onComplete is when the trade analyzer unsubscribes, and the onError is when the trade subscriber has thrown an exception on the onNext. So you can you get a callback as well. So these are the 4 methods. Now let's take a look at how does the publisher publish events? Let's take a look at that part. So here's our publisher. So we use the offer method. There's our event. Now pay special attention to this. This is the time that I'm going to wait. So if I reach the maximum buffer size of 2, so I've got more than 2 elements that have not been processed yet, then I will wait up to 1 second. I could specify more if I want. It's up to me. And what happens is that when this condition, when the message has, in other words, when the publisher has waited more than 1 second, this callback is used here. And it's a handler that says, do you want to retry or not? Here I'm saying no, so I'm dropping the message. So obviously reactive programming doesn't solve the problem of inefficient consumers, but it gives you the visibility so that you can react to these situations. And that's really at the heart of it all. So I'll give this a quick spin. And I'm purposely having delays here, and you're going to see a message dropped here. So these are some market events, stock market events, and we've actually dropped the message here because of the fact that it was too slow. So you could take an intelligent strategic response. You can retry again. the reactive programming gives you that visibility, and that's what it's really all about. So just any questions before I move on to the next two?
This is Kelly. I have a few questions here. One is, I am trying to convince my boss to upgrade our Java version from 7 to 10. Is there a convincing argument to be made?
Yeah, so we actually see that quite often. So there's a lot of people that are under the mistaken impression that they're running an old version of Java and it works, right? So that's fine. So the thing is to keep in mind is that Oracle has stopped supporting Java 7. Even if you paid for support, you're not going to get any more support there. So you're really forced to upgrade because you're not going to be getting any of the security patches anymore. No more upgrades will be done. So that should be reason enough just to upgrade. The second important reason, of course, is the fact that there are so many changes that have happened in the last 3 versions that you're missing out on all these features, especially when it comes to the functional programming side. These are, they make you program better, and you could program in a functional way and get rid of a whole class of types of errors that you wouldn't get otherwise, or you would get otherwise. So these are all good reasons to convince your boss to upgrade.
All right, another one. When and where should streams be used? Are they better suited for particular problems?
When it comes to streams, you can replace streams with any while, for loops. You can really go wholesale and change everything. Now, I wouldn't recommend when you upgrade to actually go back and change your code, your legacy code. I wouldn't do that. But once you start knowing how to use them, I would suggest to use them, everywhere in your code. You don't have to actually do the parallel part of it because as I mentioned before, there are 2 separate pieces. There's the realization of functional programming and the parallel processing. These are 2 separate things. You could just use them just to express your algorithms in a more declarative way. And like I said, you can program, once you understand how they work, you can use them everywhere.
All right, and one last question. We use lots of async programming in my company with futures. Are promises better than futures? So
the promises really, they extend the futures. And if you're just going to do regular asynchronous programming, such as, if you've got a consumer and a producer, you could just stick with that. So the promises are when you have multi-stage processing. So you've got complex algorithms that need to run one after another, and the results of one feeds off to the next. That's really the case where you want to use promises. Otherwise, you can keep on using the regular futures.
Okay, Nick, I think that was the last question. We can keep moving.
Okay, great. Thanks. Okay, let's talk about the number 2 here, JPMS. JPMS is the Java Platform Module System, otherwise known as Jigsaw, Project Jigsaw. That was added. That was a big feature of Java 9, of course. And in the Modern Java course that I teach here at ProTech, I actually spend the better part of a day going over this. It's a fairly complex topic. There's a lot that it involves, but I'm just going to focus on one particular thing of how you could use JPMS to improve your code. So what is JPMS? Well, essentially it brings native modularity to Java. We didn't have real modularity with JPMS until JPMS came. The big selling points are the fact that it gives you strong encapsulation. And that's the idea that a module, which is a new scope in Java after packages, the modules are able to protect their internals. So if you've got different modules, then a particular module only exposes what other modules should see. That's the first part. The second part is the idea of reliable configuration. That's the idea that a module is treated as an atomic whole. Unlike a jar file, which you can mix and match different classes, and then we get into the famously known jar hell. So the idea about reliable configuration is that we avoid that because modules are taken atomically. So modularity is very important because it breaks up monolithic apps. And when you're building fairly large-scale Java apps, you need that. Otherwise, it becomes unmaintainable. The other great thing about JPMS is that it also makes the JVM itself more modular. So not only do you have the tools to build your apps to be more modular, but the JVM itself, the libraries, have been made more modular. So let's focus on this one aspect of modularity, and this is Hiram's law. And Hiram's law says that with a sufficient number of users of an interface, it doesn't matter what you promise in the contracts. All observable behaviors of your class will be dependent upon by somebody. So this is an interesting phenomenon that we see. So I'm going to show you an example of what Hyram's law means and how JPMS can solve that problem. So let's say I'm a framework developer in a company and I provide a framework called framework services at the top there. I provide those three methods, service 1, 2, and 3. And I've also got a factory at the bottom that creates concrete classes. So my idea is that I'd like for you to just see this and this. I don't want you to see the actual concrete classes that are also delivered as part of my package. Now, what Here's the law is saying is that, well, these other classes are also observable. So that means they can actually be used directly, and that gets us into trouble. So your framework clients can start depending on these classes even though you didn't want them to. For example, they can see the fact that, oh, okay, there's a class called alpha implementation. I'll use that directly. Look at that, there's a constructor. I'll just instantiate that. There's another method here that's not part of the interface. Let me just call that. There's also this constructor and then this other method. Well, great, there's all this stuff here that as a client I can try to use whether you want me to or not. So how can JPMS help us there? Well, that's where the idea of strong encapsulation comes in. So you can control what you expose via JPMS. And let's just run this example together. The way you would use JPMS to solve this problem is you would do it this way. You would create a new module. You'd call it info.modernjava.framework services, let's say. And in it, you'd have a package called API. And you'd only have those two classes in there. Those are the ones that you really want the outside world to see. You'd also have another package, but that's internal. That's your implementation package. And you'd have your alpha, beta, and gamma in there. And so with that, you would create something called a module info.java. That's a new type of artifact that comes with JPMS. And it's a regular Java class, and it's where we express dependencies. So in there, I would have the keyword module. I'd have the name of my module, which is info modern Java framework services. And I'd have the keyword exports. So I'm exporting that one package called API, nothing else. What happens, you as a client now would do the same thing. You create your own module, and you would have this, again, module info.java class, and you say, there's the name of my module, info modernjava.app, and it requires modern Java framework services. So you require a module, but you export a package. That's the golden rule. Now, once you've got this set up, you can no longer instantiate any of the implementation. You can't, it's gone. You can't instantiate alpha, beta, or gamma. You can't invoke them. You can't even do instance of on them. You can't do a forname. You can't reflect them. And so that's the idea of strong encapsulation. So even frameworks such as Spring can't reflect on them. So you actually have to use special keywords to get to see them. And that's really the aspect of strong encapsulation. This works very well and solves this problem very well. Again, you can see these examples in the GitHub repository, which I'll show you shortly. Okay, got a few minutes left. Let's do the last one. This is custom runtime images. This is another aspect of JPMS. So the Java 9 introduced the concept of custom runtime images. Essentially, these are binaries that do not depend on a JVM that is pre-installed on your host. So you're essentially shipping your app with an embedded JVM and you're set. It's as if you're linking to a particular runtime. So this has a bunch of advantages. So you can actually reduce the footprint of the application. You get a faster runtime, faster startup time because you're really shipping a lot less. You're just shipping the components of the JVM that you actually use and not everything else. This works very well also with containers. So in the brave new world of containerization, this will work very well. So the way to explain this is before Java 9, we had the rt.jar file, and this was essentially it's a runtime jar that contained every library that you see in Java SE. This was a big jar file, about 66 megs, many tens of thousands of classes in there. What they've done in Java 9 is they split this up. It was a very long endeavor, by all accounts, about a decade in the making. And so we have the base module, which is your most commonly used classes. You have the utils in there and the Java langs, of course. But then you have things that are more specialized, like the XML library, the SQL library, that you're not going to use most of the time anyway. So why make them available at runtime? This is something that exists in JMod files. It's a brand new format. They're conceptually similar to jar files, but they're meant to be used in modularity and for custom runtime images. So you can also create your own JMod files for your own application. The JMod files also can hold native libraries if they have, but they're essentially used for, as I mentioned, for custom runtime images. We use that, the way we would create custom runtime images is with a new tool called JLink. So essentially you're introducing a linking phase in your Java applications. We have a few minutes left here. So let's talk about the course here where we're offering here at ProTech. It's called Modern Java 8, 9, 10, and Beyond. It's really about the modern age of Java, all these things that I talked about and much more. It's a 3-day hands-on class, but there's lots of labs. We cover mostly things that are from 8, 9, and 10. And since we're going to have new versions coming up much faster, we'll also update it with Java 11, which is scheduled for later on this year, September. The class that we have are July 9th. This is the next class coming up, July 9th to 11th, and then we have some more in October and February of next year. But of course, we can always accommodate any kind of request that you may have. So this is the repository where you can find them. So it's called 5 Ways to Modernize, and there's a README file so you could look at how you can deploy these and test these out for you. So with that, that's it for me. I'm going to pass back the control to, unless actually if there were questions, I'll take the questions right now.
Sure, so there were just a couple. We use OSGI for modularity at our company. Should we use JPMS?
Yeah, so that's an interesting question. There's actually kind of a war between the OSGI folks and JPMS. So OSGI and JPMS are very close in intent. So JPMS doesn't do exactly everything that OSGI does, and conversely, OSGI doesn't do exactly everything that JPMS does. But there is a lot of overlap. So I would suggest at this point that if you're using OSGI, you stick with it, and we'll see where that goes. But my opinion on this is that since JPMS offers native modularity, then it's much better positioned in the future to be doing modularity in Java, I would say, than OSGI. But it's hard to predict. It depends on market forces. So that's really my take on it.
Sure, and are JMod files the successor of jar files?
Yes, that's another good question. So the thing about JMod files is that so jar files are still used, but you use JMod files for linking. So whenever you're going to do custom runtime images for your own app, that's when you use them. The JVM itself ships with JMod files. That's how they chopped up those tens of thousands of classes into pieces. They use JMod files. So essentially, you use JMod files when you want to do custom runtime images. Otherwise, you can still keep using jar files for other purposes. That's really the way I would kind of split this up.
Okay, thanks, Nick. That was the last question that we had. Thank you guys so much for attending today. You will receive a survey after the webinar wraps up, and we will be shipping out a copy of the slide deck as well as a link to the recording. So if there are no other questions, which it looks like there aren't, we will let you guys go for the day. Thank you so much. Have a great day, everyone.